with this circuit, we got kind of lucky. Things happened so slowly that I could actually get away with moving the wires back and forth and leisurely watching the capacitor charge on the oscilloscope. So sometimes you don't have that option. Like if the time constant's really small, like if it's in the milliseconds or microseconds or even smaller than that, you might need a faster instrument to make those measurements. So what we could do is use the function generator. And so I turn on the function generator there. And instead of applying a step function, I'm going to apply a square wave to the input of the resistor. And if I make the square wave frequency low enough, in other words, if the period's long enough, then we're going to give the RC circuit ample enough time to charge the capacitor, and it should be almost the same as putting a step function on there. The only difference is now we'll be able to see the charge when the step goes high, or when the square wave goes high, and the discharge when the square goes low. So an example of the discharge before we connect that up, as you can see right now, our circuits are connected. So I'm connected to my positive terminal. This is from the last experiment. It discharged a little bit while I was talking, but now we're back to our basically final conditions where our step is high and capacitor is fully charged, no currents flowing anywhere. Now I could discharge the capacitor by connecting the resistor back to the negative lead, and you could do that, and now you can see the voltage decreasing across the capacitor. It's discharging. So similarly, I could save this waveform. Wait till we get far enough in. Okay, that one's saved. So I discharged my capacitor all the way, which is probably a good idea if I'm going to connect it to my function generator. Now I'm going to dial up my function generator to serve the same purpose as the battery right here. So the battery voltage was 7.8 volts. It's going to be hard to get that out of the function generator. So I'm just going to put a 1 volt peak-to-peak square wave on here. So I go over here, set the output to square wave. Then for the frequency, I might want to, well, I'm definitely going to want to choose something very low, and I might want to specify it as period. In other words, what's the time duration between the positive and the negative going steps of the square wave. And we know that the time constant was 2.2 seconds. And we know that we asymptote to a final value in about 5 time constants. We could see that here. 5 time constants is about a little bit more than 10 seconds. So we go 1, 2, 4, 6, 8, 10, around there. So if we asymptote to our final conditions, roughly, or asymptotic conditions in about 10 seconds, if we choose a square wave that has a period of 20 seconds, in other words, 10 seconds high, transitions 10 seconds low, then we should be able to see this kind of exponential behavior for both the positive and the negative going transition. Now I can go over here and dial in the period, which is going to be 20 seconds. So now I have a period of 20 seconds, and then I want to set my amplitude, and I want to set it to 1 volt peak to peak. When I do that, there's one other thing I need to do. I need to set the output of the function generator to high impedance. And when I do that, you'll notice that changes to 2 volts. And we'll fix that. Now we're back to 1 volt. We'll talk about why that happens later on. So next thing I want to do is set a DC offset, because I want this to actually be swinging between 0 and 1 volt. I don't want it to go negative because we have an electrolytic capacitor and they don't like that. So now I have everything set up. I have a period of 20 seconds, amplitude of 1 volt, and an offset of 500 millivolts. So the 500 millivolt offset is like putting a 500 millivolt constant, superimposing the waveform on that of the square wave, therefore it offsets it so that it goes between 0 and 1 volt, not between minus 500 and plus 500 millivolts. So I'm making my connections now to the circuit. I want to make sure nothing shorts out here. That would be bad. Let our function generator run. And let's see how it works. and nothing's happening. So it happens to everybody, so you have to make sure you turn the output on. So other thing is I changed the voltage, so I'm going to need to change the vertical scales. So I might want to go to a 500 millivolt scale, or maybe, yeah, 500 millivolt scale. That'll give me 2 vertical divisions. And you could see the capacitor is discharging right now. We're on the negative cycle of the square wave. Now we're on the positive cycle. And that looks kind of odd. So something's not totally right there. So this yellow trace is the voltage across the function generator output. And notice it's not actually behaving as an ideal square wave. So can anyone figure out why? So I'm going to save a few cycles of this, and you're going to analyze this as well. And here on the slower time scale, we're on 5 seconds per division. You could see the positive transition, negative transition. And note, this is supposed to be a square wave, so why is it asymptoting? So capacitor charging looks pretty good, right? It's kind of exponentially rising up, but it doesn't actually get to its final value. Like you remember in the other, when we had it connected to the battery, it asymptoted within the 10 seconds, and now it's not in this one. So what's going on here? We'll stop it and save it.